Global vehicle emission targets are driving massive change, creating demand for new electric technology that will depend on a secure and reliable supply of high-purity cobalt and nickel sulphate for this growing market. CleanTech's world-class Sunrise project is a laterite mineral resource, rich in cobalt, nickel, scandium and platinum. It will become the world's largest non-Congolese source of battery-grade cobalt sulphate and nickel sulphate, critical raw material inputs into the cathodes of lithium-ion batteries, perfectly positioned to meet the global requirements for the electric vehicle and battery market. CleanTech Sunrise will also become one of the world's first producers of industrial-grade scandium, geared for the next generation of lightweight aluminium alloys for transportation markets. Demand for the products CleanTech Sunrise will produce is already high and is only set to grow. CleanTech has been at the forefront of innovative technology for 25 years. With its proprietary CleanIX technologies, it will transform current perceptions on mining technology and processes and aspires to be a world leader in the supply of metals which lower the environmental burden. The CleanIX technologies vastly reduce the number of processing steps, creating a more economical, competitive and marketable product. With mineral resources in excess of 100 million tonnes, verified by over 1,300 drill holes, CleanTech Sunrise has an approved 20-year mine life with a resource base that could see this double. Ore will be delivered to the ore preparation circuit, where it will be crushed, beneficiated and thickened prior to entering the PAL circuit, where nickel, cobalt and scandium are extracted from the ore into a leach solution. This then enters CleanTech's patented CleanIX continuous resin in pulp process, where nickel and cobalt are selectively extracted at a high rate of recovery into a concentrated solution. From here, it moves through solvent extraction and crystallization prior to product packaging of the high-purity materials. Innovation is at the core of CleanTech's philosophy, which is focused on simplicity and technical solutions to deliver quality, affordable products to customers. Situated in New South Wales, near to Condobolin, Forbes and Parkes, CleanTech Sunrise is based in one of Australia's most established mining jurisdictions with low sovereign risk. CleanTech is committed to working with the community in a spirit of togetherness. With a vision of helping its host communities thrive, earning and maintaining a social licence to operate is a priority. The mine and processing facility is all on one site, with an operations centre to be located nearby in the regional centre of Parkes. Delivery to market will be easily facilitated through established road and rail networks to nearby ports, making export fast and efficient. CleanTech Sunrise is development ready and is unique in its potential to provide this critical commodity for the future energy market. Aggressive vehicle emission and electric vehicle targets set by China and Europe will drive significant demand for battery technology, applying serious pressure on existing global supply. With the world moving rapidly towards a low-carbon footprint society, CleanTech is at the forefront of powering innovation in this new age of transportation.
Good morning, ladies and gentlemen, and welcome to CleanTech's Battery Metals Webcast. I'm Sam Riggall, the CEO of CleanTech. I will present and moderate today's session. Today is an important day for CleanTech and its shareholders. We have reached an important milestone in the delivery of our Sunrise Battery Metals project, confirming it as one of the world's largest, lowest cost and development-ready battery materials plants. Today's webcast will include a presentation, followed by a Q&A session with members of our management team. This includes Tim Kindred, Sunrise Project Director, Peter Voigt, CleanTech's Founder and Chief Technology Officer, Ben Stockdale, our CFO, Luke Cox, Manager of Mining and Geology, Simon Donegan, Manager of Process Design for Sunrise, and Tim Langan, our Manager of Scandium Alloy Development Programs. Questions for Q&A can be submitted via the dialogue box on your screen. We will try to address as many as we can. So let's start. Today we are presenting results from the Sunrise Project Execution Plan, details of which were released to the ASX and TSX earlier this week. The Project Execution Plan was commenced almost immediately on completion of our feasibility study in 2018. It has been prepared by an integrated clean-tech Fluor engineering team to update capital and operating cost estimates, provide a revised schedule, and ensure our execution plan is delivered successfully. Most importantly, however, the project execution plan implements a design philosophy that is built on direct input from our engagement with the automotive industry. This input recognised the significant risks associated with securing large volumes of key battery metals, particularly nickel and cobalt. Risks that cannot be easily outsourced or contracted away by car makers. What did the car makers tell us they wanted? They want lower cost metal and stability in pricing. They want diversified sources of supply from lower risk jurisdictions. They want transparency in environmental and community management. They want a simpler supply chain with ease of traceability for their products. They want cradle-to-cradle mindset from suppliers that incorporates recycling. And they want to know that metals will be available in the form required when needed by the industry. It was with these objectives in mind that the Sunrise Project Execution Plan was conceived. Its aim is to implement a very clear design and operating philosophy at Sunrise, incorporating what we heard. Now let me be clear, this is not the way mines are usually built. Sunrise is a template for how two very different industries, mining and auto, can work together to improve supply chain efficiency, lower cost, and improve transparency. Ultimately, this is about protecting the enormous investments being made as capital transitions from old industries to new. Have we got it all right? Probably not. There is always room for improvement. But in our view, Sunrise is the closest the mining industry has come to defining a design and operating philosophy to meet the needs of an automotive industry that is now focused on building a completely new supply chain model for electric cars. Now let me explain what we've done to do this. I like to call this our 4 pillars. First, we have designed a flow sheet that goes direct to high purity metal salts, in this case, nickel and cobalt sulphate. It is simpler and will deliver substantially lower cost metal units into the supply chain. We are not hedging our bets with this flow sheet. 100% of our production is earmarked for the battery industry. In this flow sheet, we undertake the costliest and most technically challenging aspects of impurity removal, where it is most manageable, while the metal is in solution. By putting metal extraction with refining in one location, we eliminate transportation, rehandling and reprocessing costs. We enable traceability to one production site, and we substantially shorten an already long and complex supply chain. Secondly, the plant has been designed with one of the industry's lowest carbon footprints. This is important because nickel extraction and refining generates more carbon per kilowatt hour for battery capacity than any other raw material input. Sunrise generates most of its electricity on site from a cogen plant that captures steam from the acid plant. The balance of power requirements can be supplied by renewable energy. It should not be overlooked that Sunrise sits in one of Australia's largest renewable energy corridors, the New South Wales Central West Renewable Energy Zone. Thirdly, the refinery design now enables us to process not only the mined ore, but also intermediate and secondary metal. We can take cathode from spent batteries and recover the critical metals. As metal recycling assumes greater importance from the end of this decade, we are building Sunrise with an eye to multiple pathways to take back and regenerate our metal. Finally, as the world's largest scandium resource, Sunrise will play a leading role in the production of next-generation and military-grade aluminium alloys for applications requiring high strength, corrosion resistance, formability and printability. Some of the key improvements in EV performance will come not from better batteries, but from lightweighting. The large-scale aluminium casting and stamping technologies now emerging in the auto sector could be material enhanced by these alloys. These 4 areas have been the pillars of our design philosophy. This is what a state-of-the-art battery metals facility looks like. As you can see from this model, we have designed a flow sheet that is compact but integrated. The refinery has capacity to supply enough nickel and cobalt to support approximately 1 million electric cars a year, or about 1% of total world auto production, at extremely low cost. It will operate for over 50 years. Longer term, we expect additional value to be unlocked at Sunrise by producing cathode precursor at the same site. This is an area where we have already started technical work. Whether done by CleanTech or with an experienced industrial partner, there are significant synergies in integrating the steps at which metal salts are converted to precursor. Let me stress, this is not mining as usual. While we are producing metal, the high concentration metal salts are produced in the primary extraction circuit and refined to high purity chemical form at the mine site. This is the role mining will need to play in a renewables world. Adaptability to deliver higher value, lower cost products to simplify supply chains and lower risk. Let's now turn to the assets and the operating plan. Mineral resources and ore reserves have not changed substantially since the feasibility study was released. Ore reserves will support over 50 years of operation, although for this study we have assumed a mine life of 25 years only. There is enough nickel and cobalt in the ground to support well over 1 terawatt hours of battery capacity and 8 million tonnes of aluminium alloy production. The unique nature of this ore body is highlighted by the simple fact that, in addition to the nickel and cobalt and scandium, over 1 million ounces of platinum also sits near surface. We intend within the next few weeks to begin drilling below the laterite to test the potential of platinum group metals at depth. The mine plan now assumes a large pre-strip in year 1 and a constant 11 million tonnes of ore and waste moved each year after that. This significantly simplifies mine planning and contractor management. Mining will end in year 18 with ore to be reclaimed from stockpiles. Given the shallow nature of the deposit, at a maximum of 40 to 50 metres of depth, mining will be undertaken by a modest fleet of excavators and haul trucks. Before entering the leach circuit, ore grades will be enhanced by beneficiation to remove barren silica. As you can hopefully see from the drill core on this slide, the distinct quartz veining in the ore is amenable to separation by a simple screening process. With the price of cobalt historically trading at about 3 times that of nickel, it is worth underscoring the importance of the cobalt mineralisation and grades at Sunrise. This graph plots the ratio of cobalt grades to nickel grades at Sunrise, and it compares it to operating laterite mines around the world. As you can see, adjusting for cobalt credits, Sunrise will, on a nickel equivalent basis, be one of the highest grade and lowest cost laterite resources in the world. Not to mention the credits we achieve from scandium oxide and ammonium sulphate. Cobalt sales will generate about 30% of total revenue, making Sunrise one of the largest suppliers in the world outside the Democratic Republic of Congo. While we expect to see continued efforts to thrift cobalt in cathode chemistries, we believe the value of cobalt will ultimately be underpinned by both life cycle and safety considerations in the battery. It only takes a global product recall of a simple mechanical component in a car Think of a seatbelt, an airbag, brakes, or catalytic converters, and a multi-billion-dollar cost involved to truly appreciate the value cobalt has in managing warranty and reputational risks for car makers. As I noted earlier, all of Sunrise's nickel and cobalt production will be refined to battery-grade sulphate. In the first decade of operation, metal production will average about 21,000 tonnes of nickel and 4,500 tonnes of cobalt every year. This will make Sunrise one of the world's largest integrated battery metal plants. The refinery has been designed with a higher nameplate capacity, 25,000 tonnes of nickel and 7,000 tonnes of cobalt. This gives us the ability to maximise revenues in the future years by flexing production in favour of either nickel or cobalt, depending on price differentials between those two metals. The triangular wedge is also important. As we see a natural decline in ore grades over time, the refinery can accommodate other feedstocks, such as spent battery cathode for recycling. This can be done by progressively adding dissolution tanks to the circuit. As I said earlier, these regenerative design principles are a pillar of our cradle-to-cradle approach for cathode metals. The project execution plan also anticipates an important Phase 2 for Sunrise, which has been under consideration throughout design and engineering. While Sunrise is licensed to process about 2.5 million tonnes of ore a year, our autoclaves, pictured on this slide, are rated for about 3.3 million tonnes per annum. Our design has anticipated an increase in throughput by including space for debottlenecking the circuit on either side of the autoclaves, once steady-state operations have been achieved. What's this worth? Well, as a rough estimate, a further 100 million Australian dollars could be invested in year 4 to increase output to 3 million tonnes per annum, adding another 580 million Australian dollars of NPV at the time. It's important to note that this Phase 2 debottlenecking does not form part of the current base case or the financial evaluation for Sunrise, and would only do so once regulatory approvals were obtained. Earlier this year, CleanTech commissioned Energetics, one of Australia's leading environmental consultancies, to undertake a life cycle assessment on Sunrise. We also asked Energetics to benchmark Sunrise against other nickel flow sheets to compare carbon intensity using a standardised benchmark of performance. In this case, kilograms of CO2 equivalent for every kilogram of nickel contained in sulphate. We did this across different nickel ore sources, sulphide and laterite ores, and the different production processes, pyromet and hydromet. The results demonstrated that, even when compared to high-grade nickel sulphide resources, Sunrise benchmarks exceptionally well due to its efficiency in power generation, its high degree of processing integration, and the efficiency of leaching and metal extraction. Every step in design has been undertaken to ensure industry-leading emissions performance at Sunrise. As this graph shows, if the world is to have any hope of producing enough nickel to satisfy global battery demand for the auto industry, most of the heavy lifting will need to be done by laterite resources. Good nickel sulphide resources are geologically scarce, and they typically have short mine lives. There are simply not enough of them in our global resource inventory to support a global electric vehicle industry. What this means is that significantly higher nickel and cobalt prices should be expected if we are to incentivise development of new laterite projects. Managing industrial impacts on the environment is core to CleanTech's mission ever since our founding. We do it in our water treatment business, we do it in our innovation centre, and we do it in mining. Sunrise will build a fully lined terrestrial tailings dam to store waste from the operation. It will be built to world's best practice and utilise downstream construction methods. Water treatment facilities are also built on site to ensure process water is effectively cleaned and recycled back into our process streams. Some of our waste will also be converted to fertiliser for sale to local and interstate agricultural markets. Disappointingly, our industry is seeing several new nickel and cobalt projects in development that intend to dispose of millions of tonnes of waste directly into the ocean. Unfortunately, these projects will, in the long run, significantly undermine the sustainability credentials of our industry. While there are always technical reasons to justify operational decisions, the question is not one of optimising trade-offs here, but whether, given the environmental cost is so high, projects like this should be built at all. We are proud of the work we have done with local communities around Sunrise. While we are not yet operating and our resources are limited, we have worked with the community to find ways to support local initiatives and address concerns. Our relationships with local and state governments is transparent and, I believe, constructive. We are grateful for their enthusiastic support of our project. Once built, Sunrise will be a significant generator of employment in the region and more broadly for New South Wales. These are well-paid, highly skilled jobs that will contribute benefits to the local community for more than a generation. As I mentioned earlier, scandium is an important plank in our approach to design, not just because of its economic value, but also for its ability to completely transform aerospace and automotive markets. Sunrise is the world's largest resource of a metal that is widely recognised as the most effective and versatile alloy for aluminium, making it stronger, more formable, corrosion resistant and printable. From EV battery pack housings to 3D printable rockets, we continue to invest in alloy development programs with our partners that are expected to result in excellent demand for scandium. Like most industrial alloys, this is a market that will start small, but its potential is very large if we support customers to find better ways to make their products. Let me now touch briefly on the economics of the project. The project is estimated to cost just over $1.8 billion. This includes $168 million in contingency. While that might appear to be a large number, in the scheme of investments being made across the electric vehicle supply chain today, it is actually extremely modest. I wish to stress that this is a reliable and realistic estimate based on an incredibly thorough package of work undertaken to date, including well-established estimating procedures and a clear delivery schedule. The estimate assumes a 3-year construction schedule, plus a 2-year ramp-up from signing of an EPCM contract. If the car industry wants nickel and cobalt by the middle of this decade, projects need to be in construction today. Nickel laterite development has had mixed fortunes. Many projects have suffered from overly optimistic cost estimates and development schedules. That said, there have also been some very reliable operations, built successfully and run for many decades. For CleanTech, it's important to acknowledge and manage these risks if we are to deliver Sunrise. Over 200 million Australian dollars has been invested in the project to date to front-end load our development work and mitigate key risks. This is the investment to get us just to the starting line. It includes drilling, multiple piloting campaigns across the entire circuit, and progressive risk reviews to identify learnings from past projects and current operations. We have taken the time to assemble an experienced team with people who have worked on almost every nickel laterite operation in the world. Benchmarking Sunrise's capital cost against existing nickel hydromet operations shows that between $50,000 to $60,000 per tonne of nickel equivalent capacity is realistic in this industry. This is what it takes to build a project that meets the requirements of a supply chain focused on both cost and sustainability. If there is one message to take away from today's presentation, it is how incredibly competitive this project will be on the nickel cost curve. We are blessed with exceptionally good geology, low clay, low magnesium, and very high byproduct credits. Average C1 cash costs will be negative 80 cents per pound of nickel, over the 25-year life of the operation, and negative $2 per pound for the first decade. It is difficult to overstate how important this cost structure can be to the economics of the battery manufacturing when established as part of an integrated supply chain. Let's put this in perspective. The impact for a car or battery maker between owning a resource with Sunrise's cost position and buying the equivalent amount of nickel and cobalt on market at today's spot prices is about $220 million per year, or a saving of about $6.30 per kilowatt hour for an NMC 811 battery pack. Those savings add over $300 to the profit margin of a vehicle. This is not a small number when you are producing millions of vehicles every year. As you can also see from this slide, as prices move higher to first incentive forecast prices and then historic high nickel and cobalt prices, the potential impact on the auto supply chain is enormous. Metal price volatility will emerge as an enormous risk if you take the exponential view on electric vehicle growth. This brings me back to the issue of supply chain integration and our belief that car makers will eventually have to control their sources of metal supply. Not because they have any desire to be in mining, they don't, but because their electrification strategies are hugely exposed without it. With battery pack prices targeting $100 per kilowatt hour in the next few years, there will be diminishing areas where savings of this size can be rapidly realised across the supply chain. Without wishing to state the obvious, assets like Sunrise have far more value in an integrated EV supply chain than as a standalone mining operation. For our economic evaluation, we have used price forecasts from Benchmark Mineral Intelligence, resulting in a long-term weighted average price forecast of just over $24,000 per tonne for nickel and $59,000 per tonne for cobalt. In calculating incentive prices, Benchmark forecast nickel demand in batteries to increase from 140,000 tonnes in 2020 to about 1.4 million tonnes in 2030, a tenfold increase, and cobalt demand in batteries to increase from 52,000 tonnes to 280,000 tonnes over the same period, a fivefold increase. Tighter emission standards and policy statements supporting EV adoption underpin those forecasts. The economic outputs show a project with a strong NPV of $1.2 billion, generating on average $300 million per annum of free cash flow over its first 25 years of operation. With its low operating cost base, it is well positioned through the commodity cycle. Let me conclude by saying that Sunrise is a strong project in a great location, ready to build, and designed to address one of the largest industrial transformations the world has seen in over a century. In referring to Sunrise as a mine of the future, we don't use that term lightly. This is how mines will need to be conceived and built in a decarbonising world. I want to express my thanks to the talented and experienced managers and engineers who were part of the team that delivered the project execution plan. It is a robust and comprehensive study that positions the project for its next phase, financing and construction. While we cannot provide guidance on a timeline for funding, we are prepared to be patient. The resource is going nowhere. To us, Sunrise is an option on the future success of the electric vehicle industry, which is still in its very early stages. If you are prepared to take the exponential view on electrification, as we are confident that we've positioned Sunrise as the most strategic and development-ready battery materials asset in the industry. Thank you for listening, and we will now open up for Q&A.
Sam, we've had some questions from some of the participants on the call. The first question is, you recently announced scandium offtake contracts with Panasonic and Relativity Space. Can you give us any update on what's going on with the scandium development programs at the moment?
Thanks, Ben. Yes, we can, and that's an ideal question, I think, to hand over to Tim Langan, our Manager of Scandium Alloy Programs. Tim?
Thank you, Sam. I'll start by talking about the two exciting projects that we have with offtake. We're working very closely with Relativity Space to optimize scandium-containing alloys for the 3D printing that they're doing for launch systems. In this case, scandium offers one of the only ways to improve strength in 3D printed structures. We're also working with them to develop the supply chain required to produce the alloys for printers, which will open up other opportunities for us in other applications. The Panasonic effort is a little different. We're working with them to define applications where scandium-containing alloys can be used to both improve performance and reduce cost for consumer and electronic products. I think in addition to these applications, these announced applications, we're also working to develop alloys for aerospace and, I think more importantly, automotive applications. As you said, Sam, lightweighting is critical as the world moves to electric vehicles, and scandium offers a lot of opportunities to improve aluminum alloys. Previously, people really didn't look at scandium in automotive alloys, number of metallurgical and cost issues. Scandium from Sunrise will give us the opportunity to develop this market, and we've been working very closely with our industrial and university partners to develop applications for lightweighting.
Thanks, Tim. That's terrific. I would add to that being involved in alloy applications for space programs is a terrific and very exciting opportunity. I believe Relativity have plans to launch their first rocket next year. And the US launch industry is one that's growing at a very fast rate. So being certainly embedded within the supply chain in those industries is a very exciting opportunity for us. Ben?
Another question, Sam. You've stated reserve life at Sunrise of around 50 years. But the PEP only addressed the first 25 years of mine life. What constraints in terms of sustaining capital or permitting or anything else would need to be addressed to extend that mine life past 25 years?
Maybe if I just start with a quick response to that one. The only real constraint is around the duration of the mining leases, which under New South Wales legislation are usually granted for about 21 years. It's a very standard and often practiced procedure to renew your mining licences, provided there are sufficient reserves in the ground to maintain an operation. So for the purposes of the study, we thought it certainly worthwhile to cap operational life at 25 years. Maybe I'll hand over to Luke Cox, our Manager of Mining and Geology, to talk a little bit more about the reserve estimate itself.
Yeah, thanks, Sam. So that's exactly right. So we can go for 50 years. When we're mining, we send material straight to the mill as run and mine, but also we stockpile. So with the mine optimization that we do, we bring the highest grade forward, and that goes to the mill, and then the rest goes to stockpile. So there comes a point where there's the material on the stockpiles can start to be rehandled and put through the mill. So these stockpiles are relatively close to the mill. There's a low cost to that, and that keeps you going for literally 50 years. When you look at the comparison of reserves compared to resources, there's about a 90% conversion rate. So we've utilised 90% of our resource. Thanks, Sam.
Thanks, Luke. Ben, back to you.
Regarding recycling, do the old batteries need to be reprocessed to separate the cathode, or can whole batteries be put into the process? And is the anode handled as waste? Also, how are different battery chemistries handled? One process for each type? Sam?
With recycling, we have to differentiate between two different processes. One is very much a mechanical process, which is the activity of separating the materials that go into producing a battery. And the second is the process of chemically then separating the individual components or elements that form the materials. We're very much focused on that second process. So in Sunrise, what we have developed and built is a fit-for-purpose recycling circuit. We have very efficient leaching and metal separation and extraction processes that operate at that site. So in our view, the most optimal way to regenerate metals again from spent cathode is from these existing circuits that will be built. It makes far more sense for us to process what is effectively almost 100% metal through our system than 2% ore that runs through the system. And they may be built on separate circuits, but they will all utilise the same processing circuits. As to anode material, there will be limitations depending ultimately on cost as to how granular you end up creating your circuit to pull individual materials. For our purposes, we would be extremely focused using ion exchange to pull both the nickel and the cobalt again. And there are obviously alternatives for looking at additional circuits that could target potentially lithium and graphite as well. Bear in mind there may also be some of the current collecting circuits that also enter the supply chain. In the case of the anode, that is copper circuit, and in the case of the cathode, that's an aluminium circuit. So in our view, we have a very efficient process already built to take back a lot of this material and extract it effectively and at very low cost.
Next question. You've mentioned that CleanTeq is looking into going downstream into precursor production. Can you tell us a bit more about the work you're doing at the moment in that space? Sam.
Peter, I'll hand that one over to you. Peter Voigt.
Yes, thanks, Sam. I think one of the things that is really important about Sunrise is the fact that we're producing very high purity nickel and cobalt. And these are the two inputs needed for both precursor and for cathode active materials. So given that we have circuits that go to high purity nickel and cobalt sulphates, we're also investigating the possibility of actually, taking these materials and taking them to precursor materials, which are in generally the hydroxides of nickel and cobalt. And so we're undertaking some work at the moment to look at the cost benefit analysis of taking our very high purity nickel and cobalt into both precursor and into CAM. And that's an ongoing, research project that we're undertaking at the moment.
Thank you.
We've had some questions generally about platinum, Sam. What work have we done and how well do we understand how the platinum and PGMs behave in the PET flow sheet? And would higher grade platinum below the reserve enter the existing flow sheet, or would it have to be treated separately?
Maybe it's just some preliminary comments from me before handing over to Luke. The current economic evaluation does not include any value for the platinum that currently sits within the laterite. The current platinum mineralisation in the laterite is bound with the iron, and while it's recoverable, recoveries tend to be relatively low. There has been quite a bit of work done on this in the past to understand that. That said, the geological interpretation, which is a very strong one, is that most of the platinum, if not all of it, that currently sits within the laterite is the product of weathering of the underlying dunite or the intrusive structure that sits directly under that laterite resource. So there has been some limited drilling done in the past This area of New South Wales was once the world's largest source of platinum, and a lot of it was alluvial. There are a number of intrusive bodies in this region of New South Wales that are platiniferous. Of most interest to us was a few facts. One, very few holes have been drilled below the laterite resource into the dunite, and those that were, a number of them hit very interesting platinum intercepts. Secondly, at the time, almost no assays were undertaken on other PGM elements such as palladium or rhodium, and therefore we just don't know what else sits underneath this system. To me, it's an enormously exciting opportunity. As we've said previously, this is probably one of the best walk-up precious metal targets in the world, knowing that there's already 1 million ounces of platinum sitting at surface. Maybe I'll hand over to Luke maybe to elaborate a bit more on what we've done in terms of work to understand the system and the plans going forward for the drilling campaign.
Yep, thanks, Sam. So I guess the mode of formation within the laterite is the dunite has experienced weathering and mass wastage, and relatively the platinum is very immobile, so it starts to concentrate in the laterite, and that's where we've got the 1 million ounces. Now, there has been some historical drilling by Ivan Platts, previous owners of the deposit, and they've had some significant intercepts. So subsequent to all the historical work, we've pulled in a geochemist, Nigel Brand. He's looked at where did the laterite come from? Sorry, where did the platinum come from within the laterite? And there seems to be a core and concentration within the laterite and just on the contact with the fresh rock. And that's where we're concentrating most of our efforts. We've reprocessed all of our geophysical work for the last 30 years through Southern Geoscience, and they picked up some very good indicators and targets for us to drill. So essentially, we've looked at all the historical work and historical drilling, and now, so it's really to prove up these targets. And so the average depth for the holes that we'll be drilling will be 700 metres, so we are really going down into the core of the dunite. And locating the source of the platinum. So bear in mind, there is 1 million ounces on the surface that should have come from somewhere, and that's come from the dunite. Thanks, Sam.
Thanks, Luke.
Question. Elon Musk said Tesla wants nickel powder, but it sounds like the rest of the world will still need sulphate for their car batteries. If it turns out that other car makers want nickel and cobalt in a form other than sulphate, how hard is it for CleanTeq to produce some other type of product? Sam.
Good question. Let me hand that one over to Tim initially for comment, and then Simon Donegan.
Okay, thanks, Sam. So yes, on Battery Day, Elon Musk did state that I think the way forward for Tesla was with nickel powder and nickel briquettes. However, the battery lithium-ion battery supply chain requires high purity inputs, such as the high purity nickel and cobalt sulphate that will be produced at Sunrise that can go straight into the process without any purification. It's worth noting that many nickel powder and briquette products produced in the world, or the majority of them, contain impurities that are not suitable for direct input into that precursor and cathode process and require further purification. So there's still a very strong business case for the very high purity products that Sunrise will produce to be a key input to that lithium-ion battery supply chain.
Simon, would you like to elaborate further on any points there?
Yeah, the point of high purity really is key. Purification of nickel is, at least at the pointy end we're talking about, is done exclusively in solution, in hydromet. So as Sam said in the earlier presentation, we're undertaking that purification Once we put the nickel in solution, concentrated it with ion exchange, we take that opportunity to purify with solvent extraction prior to crystallization. So it's very efficient doing that all while we've got the nickel in solution, as opposed to existing producers making LME metal, perfectly suited for stainless steel production, but impurity loads such as copper and zinc are simply far too high for battery production. You can use that metal as a feedstock, but it would require redissolution and further purification, steps that are not required with our sulphate. Direct use of extremely high purity nickel metal is a possibility, but that is an exception to the rule and not what most of the world's metal is in. As to the question asking about alternative product forms, that's relatively straightforward for us. We make high purity solution that is then crystallized. Putting that high purity solution into a different box to make a different salt or indeed a metal is relatively straightforward. It would require more capital, but more importantly, it doesn't make much sense. Crystallizing nickel sulphate is straightforward, and importantly for our customers, they can take that high purity salt and dissolve it in water. You really can't get easier than that. Any other salt requires at minimum a chemical to dissolve it. So nickel sulphate is preferred for that reason of convenience. But really the key here is high purity. Our salts contain 80% less impurities than standard LME metal. That's a big difference.
Yeah, I think it's certainly worth stressing here that when we use the term LME metal, generally that has always been the standard and benchmark for quality in the metal industry. But we have to bear in mind that LME metal is not enough when it comes to battery raw materials. Having LME metal does not guarantee you a usable product. And in fact, at some point in this processing supply chain, there needs to be some form of hydrometallurgical treatment to get the impurities out, whether it's LME metal, whether it's intermediate products like hydroxide, whether it's other forms of intermediate. We need a process that gets it out. And as both Tim and Simon have indicated there, we have gone back to first principles to understand two factors here. One is, where is this most cost effectively done? And secondly, what are the various carbon and emissions impacts from where you do that? And there are any number of permutations you can have for getting metal units into the EV battery supply chain, depending on the type of product or the smelting or refining process. We are very confident, based on all the work we've done, that by keeping the metal in solution for as long as we can and treating it at that point for the difficult process of impurity removal is the best way to get battery grade metal units into this supply chain. Ben.
The 2018 feasibility study and the PEP both assumed a mining contractor would be used for mining operations. Have you looked at CleanTech conducting the mining operations itself?
Luke, can I hand that one over to you, please?
Yeah, thanks, Sam. So absolutely. But in the early years, we have a big pre-strip year. So what you do, you bring a contractor in with big pieces of equipment that will come in for a year. They'll pre-strip the whole area that we require for the next few years and expose the highest grade ore. Then that fleet will be taken off site. And then you bring your life of mine fleet on. So you've got a couple of years at that point to optimize what fleet you need. So you do bigger diggers, smaller trucks, bigger graders, smaller diggers, and dozers. So at that point, you say, well, this is the fleet I actually need for life of mine. And then you switch to an owner-operator model and reduce your costs further. So it does make sense to start with a contractor fleet. And when you write up your contract, you have an option at year 3 or year 5 to jump out of that contract and go to owner-operator. Thanks, Sam.
Thanks. The other thing I think is worth stressing is that this is not a complex ore body to mine. We're talking 40 to 50 metres depth to probably the bottom of the laterite. So it's a relatively simple strip mining operation or shallow pit. So I think that certainly the mining aspects of it can be managed readily. Thank you, Ben.
Sam, we've had a number of questions that are along the same theme, which if I could perhaps kind of paraphrase to throw a blanket over a number of them. The EV market sort of seemed to kick off in China and was very focused on China. But things seem to be moving now as the rest of the world catches up. What's CleanTech's general view, and how are we seeing things evolving in the EV market between China and the rest of the Western world?
Yeah, China was certainly the initiator of a lot of interest in not just electric vehicle demand, but also in the raw materials that will go to supplying that supply chain. It has been a progressively rockier road over time, as we've seen many of the Chinese subsidies that were targeted at consumers slowly reduced. And the plan is, I believe, still to be confirmed, but that eventually subsidies will progressively wind down to zero in around about 2022, 2023. And the rationale for that simply is that by that stage, the industry believes, with good justification, that the cost of an electric vehicle will be comparable to the cost of any vehicle that contains an internal combustion engine. That's certainly the cost-saving trend we are seeing both within manufacturing of the vehicles and of the production of the batteries that are also being produced. Today was an interesting day because we had the first results out for August electric vehicle sales data that I've seen anyway. Globally, electric vehicle sales for August are up 50% year on year. Of that 50%, China, August to August, is up about 35%. Europe is up about 150%. And extrapolating to battery demand for electric cars, we're up about, in August, 40% year on year. So despite the slowdown that COVID has caused, we are now certainly starting to see growth come back quite strongly. And as you can see from those numbers, a lot of it is being generated from Europe. This has been anticipated for some time. We know that European automakers have been busily preparing the launch of a number of new models in the European market. Those are still coming, and you will continue to see a number of European electric vehicle models released progressively over the next 3 years. Most of the major European automakers are expecting to have all of their models offered in an electric option for customers in the next few years. Likewise, this week, we saw a very significant announcement from Volkswagen, which goes to show the interplay that's taking place between China and Europe here. Volkswagen announced that it will be investing with its partners in China about 15 billion euros over the next 4 years, just to ensure that it has the production capacity for electric vehicle manufacturing. And hence, when I say that the capital cost of a project like Sunrise is relatively modest in the scheme of things, this is what I'm talking about. This is just one automaker who's taking a move now to ensure that its production supply chains are ready. As we've always said, to make those production supply chains work, though, you need the raw materials that will underpin them, and that's where assets like Sunrise are incredibly and strategically important.
Question, in terms of potential partners, do we see opportunities outside of the automotive industry, for example, in the mining industry perhaps?
Certainly that's been our experience with engagement. I have spent probably the last 3 years actively engaged with the automotive sector, who I think were far ahead of the battery industry in identifying the concerns around raw materials. You would think that those direct consumers of the metals themselves, those that manufacture batteries, would be most concerned and most engaged, but from certainly my experience, it has definitely been the car makers and the automotive industry who have taken the lead in this area. And that's driven by a number of factors. Some of it relates to issues around the security of supply and reputational issues associated with how metals are produced. But also you're seeing a number of car makers also recognising that there is enormous value to be had in integration, and that's why assets like Sunrise are certainly of interest. Having said that, I think as markets now are more confident that electric vehicles are not a flash in the pan, that this is actually a technology that is emerging quickly, and I referred to the exponential view, which we hold, that we are not even at that hockey stick point yet. We are still climbing slowly, but when we do reach that exponential turn, the world will look very, very different for raw materials. As that recognition has become more evident, we're seeing a lot more mining companies be actively engaged in looking at how they can certainly participate in this area. As I said in the presentation, if we are going to succeed as an industry in being able to supply the automotive sector, we have to bring something different to the table. The old mentality of dig and deliver won't be enough going forward to supply these types of materials. They are incredibly taxing with very high specifications, and the supply chains have very high expectations of how the materials are to be delivered. And that's everything that we've tried to build into Sunrise. That design and operating philosophy is fundamental to what needs to be delivered for the future.
Next question. Car makers, especially Tesla, are talking about reducing their dependence on cobalt. How confident is CleanTech that the demand for cobalt will continue to grow? Sam?
Yeah, maybe if I take that one, since I've been working mostly with the battery industry and the car makers. There is absolutely no doubt that cobalt thrifting has been underway and has been quite successful. And as you see the progression towards higher nickel intensity cathodes, you're seeing nickel substituted into those cathodes for cobalt. The first thing I would say to that is that Sunrise is a fantastic hedge, I guess, depending on whether you take a position on cobalt or nickel. What we've also seen, though, are some inherent limitations around the chemistry. So we've heard about what we call NCM 811 chemistry, a chemistry that contains 8 parts nickel, 1 part cobalt and 1 part manganese as being the chemistry of the future. It hasn't emerged that way yet, and you see actually relatively modest amounts of this chemistry or cathode chemistry deployed in applications. And the simple reason is that because of its low cobalt content, there are issues with stability that need to be managed. And you can manage that in different ways, whether it's through the chemistry or whether it's through things like the battery pack architecture and the way you manage the way the battery operates. Our view is that the market long term will probably be a lot more nuanced than people believe. There will be segments for vehicles that will require different batteries and different battery chemistries. At the high end, you will see high nickel containing chemistries with very high energy density, but which need the cobalt to stabilise those chemistries. At the lower end, the lower cost end of the market, you will find consumers who are quite happy to use a car with a lithium iron phosphate battery, for example. Much lower energy density, much lower range, but for the purposes of that consumer, it might be a perfectly adequate vehicle. The role of cobalt is important in these chemistries. The cobalt itself impacts rate performance. The way the lithium ions move backwards and forwards between the cathode and the anode, the cobalt in the cathode ensures that there's good stability of that structure to accept those lithium ions as they're delivered. The analogy I like to think of, which was prompted by Tesla, referring to the cobalt making it the cathode a very strong bookshelf is it's a difference between a wooden bookshelf and a cardboard bookshelf. A cardboard bookshelf will deteriorate over time, and those lithium ions, as they try and move back into that bookshelf, will be hindered. So the rate performance of the movement of those ions goes very much to the power of the battery and its life cycle. So I think that if you are looking for applications that require high performance, it's going to be very hard to avoid cobalt. Can you minimise it? Yes, the industry has been working hard to do it, but to eliminate it completely from high nickel containing cathodes is both, I think, unnecessary and potentially unwise. As I said during the presentation, as this market matures, the issues around warranties on batteries, these are the parts of the vehicle that manufacturers are going to have to warrant for up to a decade, become critical. And therefore, when you manufacture a battery and provide it to a car maker, you need to be absolutely sure that you can stand behind that warranty if you're an independent battery manufacturer. If you're a car maker manufacturing your own batteries, then comes back to issues, as I mentioned, like product recalls and the cost. These aren't small, easy to fix components. Once you say that there is a technical problem with the battery and you're looking at a recall for that, that is a profoundly difficult business issue for a car maker to manage.
Sam, I note that we've sort of reached the end of the scheduled session today. Do you want to maybe have just one last one about scandium market potential?
Sure.
We've had quite a few questions generally about the scandium market and what our view is on, future customers, predominant uses and growth in that market. Could we perhaps outline, the company's view on where we see the potential for scandium heading in the future?
Sure. Let me maybe hand over to Tim, and then I might just finish with some comments of my own. Tim?
Yeah, thank you, Sam. I think, typically the low supply has limited applications and basically increased the price for scandium. In addition, a lot of the early alloys had high scandium levels. We're looking at reducing the scandium levels in the alloy and also looking at applications where scandium reduces the cost of the finished product. The other one that I talked about earlier is the additive manufacturing. So I think, combining the lower cost, I think that will open up opportunities in lightweighting in automotive, in EVs, and the scandium really is one of the only things that allows higher strength in printed structures. So I think those are kind of two of the big ones that we're looking at, would be automotive and 3D printing. Also aerospace, which is typically, kind of one of the first places that goes with scandium alloys. Historically, again, the supply has been limited, which drives the price up and makes the larger companies nervous.
Yeah, this is a good example of another market which has high specification, and suppliers need to demonstrate high value in use for the products that they are supplying. So we work very closely with our development partners to demonstrate why scandium has value in their process. We stand shoulder to shoulder in their production lines, making that case. Bear in mind that scandium is an extremely interesting alloy for aluminium, not because it increases strength marginally, it increases strength quite considerably. And in many applications in automotive, for example, you could conceive of scandium containing aluminum alloys that could replace steel parts in a lot of applications. That has some really significant cost savings for automakers and efficiencies of the vehicles. And in aerospace, it's even more. I mean, the value of lightweighting in aerospace is enormous. But as Tim mentioned, this is a very small market today. We have continued to invest in it over a number of years, and as you've seen, signed up some offtake agreements for some of our major customers, with a view to scandium being recognised ultimately as a really key part of the aluminium industry. To me, this is very much the journey that a number of the ferroalloys went on a few decades ago, whether you look at vanadium or niobium in the steel industry. These are markets that started very small, but over time, as the value of that alloy in those applications was demonstrated, these were built into multi-billion-dollar markets, and having our resource as the major supplier of this material in the world going forward is fundamentally important. And I should also add, we haven't put much value for this in our economic evaluation either. We've taken a very conservative approach about what scandium might add. So I think there's terrific upside there if we keep investing and investing wisely in this space. So look, I might end there. My apologies if you've submitted a question that hasn't been answered. Please feel free to reach out to us on our website, to our general email inquiries contact, and we will be happy to get back to you if you have any questions that need answering. Thank you very much for your time attending today. I hope you found it informative, and thank you. We look forward our next update showing significantly more progress on funding and a plan to construction for Sunrise. Thank you.